We have section 3.2.2, which deals with composition and inverse functions. Of course, both topics are covered in high school mathematics, but we want to look at them from slightly different perspectives. So the first question is, how can you write the function f of x equals cosine of x squared as a composition of two functions h and g? Well, of course, if we simply let h of x equals x squared and g of x equals cosine of x, then we'll get that h composed of g is equal to f of x. Now, the one nice thing about this is that the properties of each individual function actually dictate the properties of the composition function f. So the first question is, what is actually controlling why all the values of f are always positive? Well, of course, the values are all positive since h of x is equal to x squared is always greater than or equal to 0. The second question has to deal with the periodicity of the function f of x, which in this case comes from the function g of x equals cosine of x. Next, we want to use properties of g and h separately to determine the maximum of f of x. So without even graphing f of x equals cosine of x squared, we can look and see what the maximum and minimum are by looking at the components of the function. First, we have that g of x is equal to the cosine of x. Well, we know that that varies from 1 when x is 0 and 2 pi to negative 1 when x is equal to positive pi. So, since that will ultimately end up being squared, the maximum value will be y equals 1, which occurs in 3 locations, at x equals 0, x equals pi, and x equals 2 pi. Here's simply the graph of y equals cosine of x. The last question is looking at the minimum of the function. Well, we know that the function is never negative because of what we saw in part 2. So the minimum value will be attained when f of x equals 0. Well, that occurs when the cosine of x equals 0, which only takes place when x equals pi over 2 or 3 pi over 2. Composition is also very helpful when we want to solve equations and inequalities. Suppose you have this complex equation here. If we simply do a substitution letting z equals the cosine of x, we can actually factor this, first simplify this quadratic equation into this equation here, simplify this complex equation into this quadratic equation here, and then we can factor it and attain that our values are when z equals negative 1 and z equals square root of 3 over 2. And so we have that our actual answer occurs doing another substitution when x are the values listed here. Next, we talk a bit about the inverse of real functions. Of course, generally in an Algebra 2 course, you talk about inverse of functions, and then you teach them this step-by-step procedure where you usually say interchange x and y and solve for y and so on. And so that's how you obtain the inverse of a function. Well, graphically here, if we have y equals 3x minus 6, then the inverse is simply x plus 6 divided by 3. And here we have the graph of those two functions. And what we see is that those two functions are actually symmetric about the line y equals x. Because of that, we have these two conditions, that one, the graph of f inverse is simply the reflection image of f of x across the line. In this case, of course, that should be y equals x. And the horizontal line test actually stems from the vertical line test, because when a vertical line is reflected across the y equal x line, you get a horizontal line. So we use the vertical line test to determine whether something is a function or not. You can use the horizontal line test to determine whether or not a function has an inverse. One of the most popular examples of inverse functions, of course, is exponential and logarithmic functions. So here we have the function y equals a to the x. Of course, a has to be greater than 0, a is not equal to 1, and we have y equals log base a of x. The definition of log, of course, is y equals log base a of x if and only if a to the y equals x. Here's some simple examples you can look on by your own time, just to show how you actually compute the log. Probably the most interesting thing that we don't actually dive into too much in mathematics in high school are the properties of exponents and logs. We talk about them, but the reason that all these logarithmic properties stem from actually comes from their relationship with the exponential properties. So here I've laid them side by side, exponent and log properties, and here I've added 2 additional. We'll actually explore some of these log properties now. Later on in the semester, we'll look at some student work dealing with these exponent properties. So here's 2 examples of additional properties. A to the log base a of m equals m. Log base a of a to the r equals r. We teach those properties, but what's really nice is why those properties are true. Those properties are true stem from the fact that they are inverses of each other. Let's look at the next slide for the proof. The question is, why are the above properties true? Let's look at property 1 first. Alright, we'll start off by simply looking at the left-hand side of this equation. A being log base a of m. Now, we're just going to let y equal log base a of m. We could have chosen any letter. For right now, we'll just choose y. Well, once we do that substitution, then we can rewrite our original statement here, rewriting the exponent instead of log base a of m. We're going to write it as y, because that's what we called it. We could have called it R, Q, P, any letter we wanted to. Once we do this, we then use the definition of log. Well, since we said y equals log base a of m, what that means is that a to the y has to equal m. Well, now we can do one more substitution. We have a log base a of m is equal to a to the y. But again, because that's how we define the log, based on the definition, we get that that's equal m. So that's why that property 1 is true. Property 2 is much easier. It follows straight from the definition. If y equals log base a of x, we know that that means that a to the y equals x. So if log base a of a to the r equals r, then that means by definition that a to the r equals a to the r, which we know is true, so that rule must be true. Now let's look at the proof of this property. We teach it all the time, and that is the log of a product is the sum of the logs. That's usually how we do it for shorthand, but why does that end up being true? Well, we begin by letting each log on the right-hand side be equivalent to something. We could choose any letter we want. So this log on the right we call m, so log base a of x is equal to m. Of course, that means that a to the m has to equal x. And here we say log base a of y equals n. That means a to the n equals y. So our first step is just going to be to start to the left-hand side, and we want to, of course, conclude with the right-hand side in the proof. On the left-hand side, we have log base a of xy is equivalent, and then we simply substitute in what we've indicated here. So instead of log base a, we have a to the m times a to the n. Now, what's very nice here is you see that the way we're going to get to the right-hand side is really by using a property about exponents, which is that a to the m times a to the m is simply a to the m plus n. Once we do that, using a property on a previous page, we know that this is simply equivalent to m plus n. And so we have that log base a of x, because that's what we said m was, is equivalent. And then n is simply log base a of y. And so we've proved that property. That concludes the summary of the section 3.2.2.